Okay, so today we discuss how to think of module forms geometrically. It should be very easy today. We'll have to discuss this. So let's start with the easy theorem. So this part, since we have only limited time, so I'm going to be a little bit sketchy. So H will denote the upper half plane, namely the complex numbers with a positive imaginary part, right? And Y1n is the upper half plane quotient out by the action gamma 1n. This primary. Actually, it's a good habit to write quotient the other way to indicate that I'm quotienting out a left action. Parameterizes all curves over C together with an n torsion point. And explicitly, for a point in the upper half plane, the elliptic curve, it parameterizes together with n torsion point, which I write EZ being C modulo Z CZ, and taking so 1 over n as the n torsion point. I'm gonna, because I really didn't explain what parameterizes means, so I'm just gonna give a quotation mark proof. Illustrates somehow roughly what this statement entails. I guess next lecture, when we get to the algebraic theory, will be a little bit more explicit. So know that. So maybe the first question is that it's just a relatively easy fact, which I'm not going to prove, is that every elliptic curve E over C together with an n torsion point is isomorphic to one of this kind. Okay. I guess first of all, you can adjust a lattice to be so, and at n torsion point you have a few choices, but then you can always make some sort of changes to make that torsion point to be represented by 1 over n. But let's sort of just talk about the other case. Talk about every elliptic curve is isomorphic one of this, but there might be more z's that can represent the same thing. So that's to say, if this EZ is isomorphic to EZ prime 1 over n, then I want to say that I want to show that Z prime is equal to AZ plus B, CZ plus D for ABCD in gamma 1n. Okay. So that means that combining these two, you will see that for every elliptic curve, it's of this form, and the choice of Z is not quite unique, but it's unique up to the action of gamma 1n, and therefore all such elliptic curves will be precisely given by the upper half plane H modulo gamma 1n. So let's just quickly verify this. So if I have an isomorphism as so, let me change the z with z prime. So z prime this way. Doesn't matter. So now I have a map from phi. Call it phi. This is an isomorphism. And if we look at the sort of on the tangent space of this map, it must be given by multiplication by a complex number. Because it must fix the origin. It must send 0 to 0. And then because it's a group homomorphism. So therefore, and also fixing it's a group homomorphism. I guess on the vector, on the tangent space, it must be a linear map. So this phi okay. Maybe we just say that somehow this phi must lift. It's C to C. Okay, kill that. By looking at the tangent space. So therefore this futility is multiplication by some W. Then if this futility is given multiplication by W, then the 1 on the left hand side must be mapped to W. And then Z prime must be mapped to W Z prime. On the other hand, 1 is a generator of the lattice, which must be mapped to a generator of the lattice. So I'm gonna denote this by CZ plus D, some linear combination of the element of lattice. Whereas WZ prime, I'm gonna denote by AZ plus D to be another sort of basis of the lattice. Well, such that because I guess AB, because AB and CD, they kind of form a basis for the Z2 lattice. Therefore, ABCD must belong to SL. Must belong to GL to Z. And also, there's a orientation issue. You can in fact show that this belongs. Sorry, I didn't prepare this, so I probably won't be able to do it now. So there's also a kind of orientation issue of this. Hold on a second. I should just know it. Sorry, I can't remember. Yeah, I think some imaginary numbers. Yeah, I don't remember the formula. So, okay, let's leave this as this, like that. We'll see. So at least this will tell you that Z prime is equal to, if you divide one by another, and somehow I think the imaginary part of Z prime, I just don't remember what precisely that formula is. Well, let's compute it. Anyways, let's compute the imaginary part of Z prime. So this is AZ plus B, CZ plus D, minus CZ bar. Hold on a sec. When I compute this, I have to divide it by 2i. Hopefully this won't turn into a disaster. Okay, and then what is this? This minus this. Okay, this is BC minus AD. Yeah. Times C bar minus C. Okay, good. Because I can't remember it's a determinant times this, well, I mean, AD minus BC is a determinant, but a Z minus Z bar over 2I is imaginary part of Z. So this is sort of AD minus BC. But as the imaginary part of Z prime and the imaginary part of Z are both positive, that shows that AZ minus BC is positive. Okay. Yeah, I'm a little worried about this. Good. Okay. So good. So after it's done, so this only tells you that you have this lattice, you have the basis of lattice over here mapping to the basis of lattice on the other side. That already tells you that this ABCD must belong to SL2Z, the change of basis, or rather somehow the relation that between Z prime and Z satisfy this condition. But we also have to want to know that my ABCD belongs to a smaller subgroup, gamma 1n. So that's where this particular n torsion point plays a role. Namely, that I have to map 1 over n to 1 over n modulo Z direct sum with Z. I.e., I want to see that I map 1 over n to the other side, so I'm multiplying by W. So this is congruent to n1 modulo Z. Okay? But my W is CZ plus D, so CZ plus D over n is congruent to 1. And this is directly, you can easily see that. This just tells you that C must be congruent to 1. Oopsie, sorry, C must be congruent to 0, and D must be congruent to 1 modulo. And so therefore, sorry, I'll just leave it here. Thus, ABCD belongs to gamma 1n. So that means that if we have an inner curve with an n torsion point, you can show that it can be written as this form. It's the curve at 1 over n. And such writing has some ambiguity. Namely, you can write it as Z or Z prime, but the ambiguity is really given by Z prime. Well, the two parameters Z and Z prime must be related by some sort of Mobius transform by some element gamma 1n. And so therefore, all possible the curves over C with n torsion point must be parameterized by H modulo gamma 1n. Okay. Quickly say that similarly, if I write y0, I'll probably mod gamma not 0. This will parameterize all elliptic curves over C together with a sigma. A subgroup of order n. And explicitly, we have a Z in here. This should correspond to the same curve I just wrote down earlier. And the subgroup generated by this 1 over n. So I write it as 1 over n Z mod Z. It's a natural second subgroup of the inner curve. In fact, we have a family. Of elliptic curves. Let's say that I have E. So this is pi. I'm back to the E1, and so therefore there's some sort of 1 over n, this point here. You have some sort of universal object, and over Z is given by 1 over n. And then, of course, I want to mention that there's a E, which is the 0 section. Just basically sets to the 0 point over Z, EZ. I want to give it a parameter. We'll see what way do I use. So I want to write, whenever I write this elliptic curve, and especially this family, this C, I want to write this C tau, in the sense that the parameter for this C, the component, the sort of added coordinate, C, is given by tau. It's tau plane. And it's quotient of tau plane by the lattice generated by 1 and Z. That'll be useful later. And I want to understand the relative differential. And because we see that this elliptic curve is sort of flat, you can just write it down very clearly to see what it is. So this is 1, 0, Z, right? Just basically gluing opposite sides of this to get a torus. And on this sort of this tau plane, it's sort of entirely flat. So there's a global differential, standard global differential d tau on that, which is invariant under translations on this curve. And all the differential forms on, or maybe I should start with this one. So omega 1 of E. How should I put this? Right. So I want to say that EZ over C is the same thing. It's a free sheet, literally a free sheet, not locally free. It's literally a free sheet with generator d tau. And if you do this in family, so this is locally free, because somehow physics, because it's free on each of the fibers. Locally free of rank 1. And I want to set omega to be the pullback of this sheet along the 0 section. In the sense that over here, what I'm doing is here I look at sort of the stock at tau equals 0. This is just C times d tau. Okay. On each of the fiber, I only look at sort of what's happening at the origin here, and I pull that sheet back from this. This is local. It's basically on the fiber. It's all free. It's a free sheet, and I pull it back along the 0 section of this one to here. And this is also the same thing as, if you want to say, this is also the same thing as global section. In other words, this is the same thing as H0 of. That's the same thing. Because free sheet, because it really is literally a free sheet. Somehow the stock at one point would determine what this sheet looks like. Right. So this omega is very important for us. In particular, because you're pulling back a line bond. Because, as I said, it's a locally free sheet for rank 1. So this omega is a line bundle. On Y1. A line bundle or equivalent, a locally free sheet for rank 1. Same thing. Now on geometric interpretation of these modular forms as follows. You see that the classical forms are nothing but sort of sections of these line bundles. So let's do the version 1. So version 1 will work over for all weights. So let's see. So let's kind of draw this picture here. So let's just say this is y1, okay? And just bring my surface. It might be missing some. It might be missing some sort of cusps, some pulp. Like maybe missing some points here and there. Okay. At each of the point x, say, just means z, the fiber of this one is in the curve EZ. If you do another one, E prime, B prime, it might be another curve E prime, so on and so forth. So on EZ, the canonical differential is d tau, right? As we discussed, it's an invariant differential. But then we know that it's possible that I shouldn't use the, let me erase c prime. But as we use the isomorphism, EZ prime goes to EZ, which will send tau prime to. So remember that we just discussed on this board that EZ, if we have an isomorphism from EZ prime to EZ, it will send tau prime to W times tau prime. To maybe say tau equals W times tau prime, which is by our definition of W, this is CZ plus D tau prime. Okay? So thus, d tau prime will be set to, in terms of, thus, if you have d tau over here, I can pull it back to CZ plus D times d tau prime. In terms of under this isomorphism, d tau would correspond to CZ plus D times d tau prime. Oh, sorry, I have d's, but anyway. So now, if have a modular form, app of weight k, level 1, gamma 1n, and we define. I can define the following. Maybe the best way to understand this is that I want to think of this as, I want to define it over the entire H. So over H, we have a well-defined EZ. Okay, so this is a universal cover. This is quotient by gamma 1n from H down here, or rather, but over here I have a d tau here. This section here is not quite invariant under gamma 1n, but because gamma 1n will take EZ to EZ prime. At the same time, it will take d tau to CZ plus D times d tau prime. So therefore, this section dz is a nice section upstairs. It's not quite invariant under gamma 1n. In the same way, when we talk about modular forms f, it's also a form on H, but not a function on the base, because it's not quite invariant under the gamma 1n action. Now what I'm going to do is I'm going to combine the f and d tau together to get something that's invariant under gamma 1n, which can be defined downstairs. So let's do that. So let's do upstairs. So if on the EZ, I associate at the prime Z, I will associate the following expression: Fz tensored with d tau to the kth power. Okay. We know that this is isomorphic to EZ prime, where we're associating Fz prime tensor with d tau prime tensor with k. But we can, because F is weight k, and we know how d tau prime translates to d tau. So therefore, Fz prime, and at this time, and also at the same time, Z prime is AZ plus B, CZ plus B, as we discussed. So therefore, this Fz prime is nothing but just, oh, okay, not doing anything yet. And the d tau prime here, when I write it in terms of d tau, you have to divide it by CZ plus D. 1 over n d tau. And by the translation formula for F, this is nothing but, oh, sorry, tensor with k, because I'm doing tensor k's power. So without tensoring, it's just d tau over CZ plus D. And when I tensor with k, just its vector powered by k's power, raised by k's power. So it's the same thing as Fz d tau. In other words, if I write instead of writing the function f or d tau, I write this expression that Fz tensor with d tau to the k. This is indeed a, so this is, it's indeed gamma 1n invariant. So Fz tensor with d tau k defines a section of, so I can, originally it's some sort of function or some expression upstairs, but now I can define, I get a section downstairs of the sheaf omega tensor with k. So namely, I record the differential sheaves upstairs. So i.e. I do this. So that's version 1. So let's talk about version 2. It's sort of similar, but this version 2 kind of only works when k is even. So the version 2 doesn't involve the universal elliptic curve. It just involves this sort of this yz itself. Excuse me, the y1n itself. Here's what we note. Is that on this y1n, if we consider Fz dz tensor with k over 2, this expression, this on H is invariant under gamma 1n action. Well, indeed. If I write this expression, if I use gamma 1n to act on this Z, So this is the same thing as CV plus D to the kth power fz. And this guy, I take the differential of that, so that's what is this? Whole thing to the k. So this returns to the calculus. Cz plus d squared, derivative of the top part. So it's a times cz plus d minus c times az plus d. So basically ACZ kills with ACZ here, so this is just basically AZ minus EC, which is 1 on a denominator. And the numerator, the denominator is just CZ plus D squared. So you see that the CZ plus D to the kth power kills this denominator, and that just gives you, there's DZ inside. So that gives you FZ. So we have two ways to think about this. So I have two ways to think of module forms. Alright, FC DZ tensor k over 2 times. So this is a section of the differential forms. This tensor k over 2. Okay, you can say what's the relation between this and this, right? It looks like your module form belongs to. You have two ways to see to see module forms. Of course, there's obvious answer to that question, and these two ways must be somehow the same. Here's a remark. It's called Collier-Spencer. Is that there's a natural isomorphism that this line bundle here, if you square it, is isomorphic to omega 1. As so. To show this, you can essentially use the same proof we have over here. Basically, over here you have this d tau. Basically, what you want to do is in some sense, somehow you basically send d tau to send d tau squared to dz and check that this isomorphism is invariant under the gamma 1n action. That's essentially what we did here, except that you see that the d tau, this translation of d tau has this factor cz plus d, and this translation of dz has a translation factor cz plus d squared in the denominator. So therefore, these kind of must match. Okay. Well, but on the other hand, we have to be a little careful that my y1 is not the entire sort of complete algebraic curve. It has some sort of missing points, the cusps. So therefore, if I really take the section of a line bundle on this one, it's going to be infinite dimensional. That's a little bit annoying when you work with this. So in particular, this space on the right-hand side, as it's written, this is not a finite dimensional, it's infinite dimensional. Because in the projected curve, if you remove a point, you get affine curve. Affine curve, the global section is infinite dimensional. I guess. So now I have to talk about extension to cusps to complete it. This is where I'm gonna get a little bit sketchy, I guess. Well, let's see. So basically, for any smooth algebraic curve, I can complete it into a sort of complete curve. In this case, I just join a couple of points. Let me use C to denote a set of cusps. here's the explicit way to write these cusps. So the y1n is upper half plane quotient by gamma 1n. The cusps can be written as p1q modulo gamma 1n. Okay, that's how I think of this. Right. If you want to find a little bit of similarity between these two, I think it makes sense to think of this H as a part of P1C. That does make sense. And in fact, somehow, I guess, and in fact, of course, so when we talk module forms, we tend to think about upper half plane. But there's also a theory that, maybe I should say this. So there's a thing called upper half plane quotient by SL2Z, right? That's what we're kind of mostly working with. But there's also a theory called upper and lower half plane quotient by GL2Z. These are really sort of the same thing. Because GL2Z, those with, SL2Z have index 2 in GL2Z. Because if a matrix is invertible, its determinant must be also invertible in Z, which must be plus minus 1. So those with determinant negative 1 will turn upper half plane into negative lower half plane. Okay. So this H, this is the union of upper half plane and the lower half plane. I can rewrite this as C minus R, or equivalently I can write P1C minus P1R. I can't quite say this is coincidental that, I don't know, maybe it's a little coincidental that this is P1R, this is P1Q. I guess it's a little coincidental, not entirely. In any case, whenever you're given this, you can supposedly count the number of cusps you have to add to this picture. But I'm just going to draw some pictures as a fact. So the way, remember that we have a universal infinite curve over this y1n, which is constructed explicitly, and also there's a section, the zero section, and this infinite curve can be extended to the complete curve as follows. But this one is no longer an elliptic curve because as a cusp it's not as bad. So I want to write this. There are two versions of extension of the curves to the cusp. Let me explain. Such that over each point x of the cusp C, we have so-called generalized, or maybe it's called Z, generalized elliptic curve. How should I put this? I'm a little hesitant to how to write this, so anyways. Let's just write this. So I'm going to call it E bar Z for the fiber here. Let me say it looks like a so-called cusp. It's a elliptic curve, but with a, I guess technically I shouldn't call it a curve, but you can think of it as sort of a singular elliptic curve with a kind of a multiplicative, with a node here, or sometimes more things here. So each of this curve, you normalize this as a P1. You're gluing sort of different P1s together, but in a kind of an n-gon shape. This is the n-gon for some n. the shape of this harmonic gons will depend on which cusp you're at. I'm not going to say too much to that. Without preparation, I won't be able to know. Somehow the smooth part of this, as you can see, this is basically this removing all the intersection, or removing all the singular points. Namely, you remove these intersection points. Especially if you're in the P1 here, you remove 2 points. I guess you can always relabel them into 0 and infinity. So therefore, if you remove 0 and infinity, this becomes GM. So this is disjoint union of GM. Or rather, this is bad. So let me write GM cross Z mod NZ is a group scheme. So this is something we should actually expect in the sense that this elliptic curve has a abelian group structure. When you degenerate a abelian group to something, that thing should have some sort of group structure. So what we're having here, we're degenerating elliptic curves to some GM. Well, possible degeneration. So when you have this, how should I put this? Or if you like to draw the picture here. So this is a curve. But when you degenerate, it may degenerate into something like this. Into like so. So like you have this curve, you have somehow there's 4 points in there, and you dip them into 1 point. Each one of them looks like a P1, and they intersect in a way like so. And then the group structure is that this each P1, remove these 2 points, kind of becomes sort of a GM, a group action. And this I should say this EZ is a group. Not only this one, but the entire thing is a group scheme over X1 and this X on. Right. Now we have this zero section of the elliptic curve as so. At the good points, at sort of the smooth point, you have just usually the curve. But you also have a section here. This corresponds to when you have this GM here. These components here, you have some labeling. So maybe one of the components is labeled 0 and 1 and 2 and 3 and 4. If you want 5, somehow the 0 will be the 0 section of this group scheme. Will be the identity element of this group. That's say 1 on this component and 0 on this component. So that means you're here. This is the E of. So note that this is going to be a smooth point because you're going to avoid those. You're removing 0 and infinity, and 1 is a point in the middle. So it's a smooth point. So that point may be somewhere. And then, remember that we have 2 definitions of omega. The omega defined by pulling back makes sense. On this relative group variety, the relative differential is still one-dimensional. You pull that back along the 0 section. And there's also a version of, I think there's also a version of this by pushing forward along this pi of E bar. I don't remember it off the top of my head, but there is a version you can also write it as one to another thing. So this is how I'll give you some sense of how this differential sheet extends over to the cusps. And over there, I talk about Cauchy-Spencer isomorphism, which is sort of omega squared being isomorphic to what you have on downstairs. But that's over the good locus. In fact, this Cauchy-Spencer isomorphism will extend to x1n as well. It will look like the following. We try not to erase this one. Same thing as so. Here I put x1 and 1 over c with the log pole as c. I'll explain on this board here what that log means. So here, this differential. So this omega is a differential sheaf allowing long pole activity. I.e. that if you look at somehow, let me just draw a picture. You have a cusp, say C. Near this cusp, I can have a parameter. So let me say if QZ is the local parameter at the in C, C, at this point in the cusp. So this omega x1n 1 log C can be thought of as sort of the usual one. Let me write it this way. So in a some sort of small neighborhood of U, in a small neighborhood of this point, it looks like sort of all the possible differentials. Let me write omega. Oh, I don't know. Just say omega. But anyways, it's a usual differential forms. Sorry. Writing is bad. For some, it looks like some sort of omega plus some alpha times dq over q. Some alpha is like so. In the sense that it allows it to have because this omega is something else. Is there someone maybe we could just write fq dq. Okay, it's some sort of another function. In a small neighborhood of that, it's just some sort of regular differential, but then you allow it to have some sort of log pole. You allow it to have some a pole here. The reason it's called a log pole because this is something we don't all know this. You can formally write it as d log q. Okay. Although of course algebraically you don't write it that way, but whenever it's dq over q, this is some sort of d log. So that's why it's called log pole here. Let me remark that also in one-dimensional case, what we have over here, because this is our case anyway, so this log of C is simply just the differential form tensor with OX1. As so. So it's just basically allowing to have some pole here. But in higher dimensional case, if you write a variety and log of a divisor, this will not be the same thing as this, or especially at the intersection point of the divisor. Okay, I'll stop here and then continue afterwards. Or earlier, so let's speed up. So now, once we discuss this, I can give a geometric interpretation of modular forms that weight modular form of level gamma 1n is just a global section of, now I can take the complete curve and omega to the power. So this will include the information of sort of being bounded at cusps. And if you want your form to be a cusp form, you need to force your section to vanish at the cusps. So you twist minus c here, so that this section will be a section over here which vanishes at c. So when k equals 2, sorry, erase the Collier-Spencer isomorphism. Now if you interpret what we have over here, M2 gamma 1n is equal to H0 of x1n of omega tends to, okay, omega tends to now can be replaced by the differential form. Differential form log c. And if you want to talk about the cos forms, that's precisely just that differential forms. And so, okay. So we'll be mostly working on this one for later. Okay, and also I wanna mention that whatever I write here, I kind of need n to be greater than to the 4 to avoid some sort of elliptic point, elliptic elements like gamma 1 and such. And also I also have a gamma not 0 version, but that's under the requirement that k is even. Okay. So Heck operator. After interpreted modular forms, now I have to discuss the Heck operators. I'll just discuss as much as we need. So say P does not divide n. And in fact, I will discuss this for gamma not n, because gamma 1n, there's a little bit of annoying thing here, so that I can't quite make it explicit. So let's do the x not n first, and I'll explain how to deal with the. It's not that big deal. I'll discuss how to modify the discussion to gamma 1n. So that's z mod goes to z and pz to be the two natural map from gamma naught. So x naught pn to x naught n. And this would correspond to if you have the curve EZ, and this is a subgroup 1 over z over z, and then a subgroup. This is a cyclic subgroup of order p. And if you map it this way, we'll just basically forget the. We'll forget this cyclic subgroup order p. If you map it the other way, so let me take a look at it. Why do I need? You know what? Let me write gamma 1, and that's okay. I've decided just that. It's like 1 over nz. So maybe I just write a general. It's kind of a general point Pn. It's a point of exact order n. Such that Pn. When I use projection 2 to go to the other one, I quotient out my elliptic curve. I just forget. Quotient my elliptic curve by the cyclic group of order p. And now this n torsion point, I mean the image, maybe just write image of this Pn in this E after projection. So because n and p are co-prime, so Pn will continue to be of an element in the quotient by C of precise order n. So these are two natural maps. Let me write alternatively. Excuse me. Wait. Another way to write this is that instead of writing this, this is also sort of equivalent to the following data. I have an E, and I have a cyclic isogeny of order P, together with a Pn of E. Basically, this E going to E mod C, and mapping this way will send this to E, and mapping this way will send to E prime. So version 1. Remember that we talked about two versions of modular forms. So in version 1, here's how we see the differential operators. So we know that so if I change it to gamma 1, this has to change it to this. Okay. I really want just gamma not anything bigger. So on this gamma 1n intersect with gamma naught p, we have an isogeny that we have over here, dot cos b, from universal E1 to, maybe I should write pi, pi 1, pi 1 upper star universal E to pi 2 upper star universal E. Right. So pi 1 upper star universal E will give you the E here. And if I pull back the universal elliptic curve using pi 2, I will get the E quotient by C. So the natural isogeny goes from pi 1 upper star E to pi 2 upper star E. So then this will imply the differential form I can pull back. So we can get a pullback of this of the relative differential forms from 2 to this from 1 to differential form. Let me do something that's sort of nonsense. I'm going to put subscript 2 and 1 here to indicate that where they come from. They're just same thing as omega, but just in case we get confused, let me just write 2 and 1 here. This means nothing. Okay? I just want to indicate where they come from. Otherwise, it's a little bit confusing, at least for me. Now I want to define a hack operator called TP naive. It goes as follows. So I want to start with I guess, on this side. So I have a global section of x1 and c. Excuse me. Omega 2 k's power. Okay, so that's where they are. How should I put this? This is where the number. So if you see this omega 2, you know it's on the right hand side from the pi 2 pullback. So if I have a section here, you can pull it back to a section on upstairs. So I have a section here. I can pull it back to a section here. Now I apply this V star, V upper star. And now I kind of get to kind of a left-hand side, in some sense. We're still upstairs here. Now I take so-called trace. Yeah. So that's why I insist on, separating omega 1 and omega 2. Otherwise, we just don't know where things come from. Okay, so that gives me a map. So trace means that somehow, I guess, if you think it complex analytically, you can take a local disk here. Upstairs, it will be sort of p plus 1 disks. You just sum up the sections there. Yeah. And I can define that Tp to be the 1 over p. You have to normalize a little bit by 1 over p of this map. So then you can think of this as sk of 1. So it's an exercise to verify this agrees with usual definition module forms. Okay. Any questions about this? So it's like you have this picture here. You just pull back and then push down. And version 2. I'm only going to do it for k equals 2. So I have exactly the same picture as before. But then now I want to realize it. I want to realize way 2 modular forms as global sections of the differential form. Then, in fact, I can think of Tp as the following. I still start from the right-hand side here, down here, this lower right corner. And then apply pi to upper star. I can pull back differential form here to here. It's a little too long, I'm going to write. And then I can trace it down. Okay. Except there's one small subtlety here that I don't need to normalize for differential forms. So I thought about it, and what's going on is that I think, and I guess let me sort of, again, kind of exercise. Check that this is compatible. With version 1 under Kodar-Spencer isoform. Okay. So there are two versions of this. One is using orthomorphic line bundles. The other one's using differential forms on these two. Let's see, what do I want? So I'll have this here. So my goal of today is to try to set up things to discuss sort of how should I put this? So my goal today is to try to set up things so that we're going to talk about how to associate Galois representations to modular forms when weight k equals 2 algebraically. Today we were only mostly working with C over C, but this will be sort of the prototype of what we do for the Q story. And so let's sort of turn this picture and make it into sort of when we talk about the Jacobian. remember that for way 2, we discussed that the way to associate augmentation to eigenforms is through taking the Jacobian of the modular curve. So now I have a correspondence, in some sense, between modular curves. I can talk about what happens to the corresponding Jacobians. So let's make things a little bit more explicit. Now I have this TP operator, this TP operator defined this way. And now let's take the dual of that and see how that compare with the first homology of these. Think of this complex, this complex algebraic curve. So for modular forms, I guess the Heck operator goes on the top level here. Let's take the dual of that and then discuss. So if I take the dual of that. So it's twice I1 dual of that. Pi 2 upper star. Okay. And remember that we have this homology. Or we introduce Jacobians of the curve. So inside of here, and similarly we have sort of similar maps of these on the homology, and all of these are sort of compatible because we have a correspondence, right? We talk about whenever I have a map this way, I can pull back differential forms, and also sort of that's also compatible with push forward of sort of first homology. Similarly here, when I push down the differential forms, the dual of that is compatible with sort of pulling back sort of once. One cycles. So this is all compatible. Therefore, this will give me maps on the corresponding Jacobians. Or by definition, I guess, this is a Jacobian for x1n. We're just gonna, it's traditional just write J1n. These are morphisms between abelian varieties. In particular, this I guess this, in some sense, this TP check will give an endomorphism of the Jacobian. So here's the upshot. What we're trying to convey is that somehow way 2 modular form. So this will surject down to J1 of n. And over here I have TP check action. It's compatible with TP check. So the Heck operator action on the dual of this differential or dual of the way 2 modular forms induce a Heck operator action on the corresponding Jacobian. Moreover, for curves, we'll have something a little bit better than that. So need a little bit of a very simple Hodge theory. For any smooth projected curve, x over c. The Hodge theory says that the first cohomology of the curve, or tensor with C, that has a Hodge decomposition this part is supposedly to be h1 of x ox, but that can be identified with the complex conjugate of all the different sort of anti-holomorphic differential forms in some sense. Sort of 0-1 forms. Excuse me, 0-1 forms. So, if you're dualizing this, this homology is going to be the same thing as in particular h1 of x1n z. Did I say this is the same thing as h1 of Jacobian? So somehow the Jacobian the first homology of Jacobian has two parts. If you tensor with C, one part is the dual of the dual with weight to modern form. The other part is a complex conjugate of that. What can we deduce from these? Well, first of all, for the least, at least for weight 2 case, we know the eigenvalues of TP are algebraic integers. That's not quite clear from, when you talk modular forms, that's not very clear. But once we have this relation here, it's clear. This is because this TP will take h1 of x1 z to h1 of x1n z. So both sides are, h2 is a, so TP check is a, what? TP check is a endomorphism of a, so this belongs to some endomorphism of some z to the r, right? So all the eigenvalues of TP check, so all eigenvalues of TP check on h1 are algebraic integers. Via that isomorphism, using this isomorphism here, now we know the TP action will preserve both sides, and the eigenvalue you see here must be one of the eigenvalues you see here. So are algebraic integers. So that's all I want to say about TP. I can simply define UP. Basically, when P divide N, that's basically sort of the same thing. In the sense that you start with your x1n, you do x1 intersect with gamma naught MP. And upstairs you have an E, a Pn, and basically a little bit more than that. So this is going to be C inside E. So this is cyclic of order. Let's say P to the n exactly divide m. So I just need a little bit more than that. Or that's the same thing. I mean, it's the same intersection as P to the m plus 1. And on the left, you just forget the cyclic subgroup. On the right hand side, you quotient out by sorry, it's not a quotient. My bad. My bad. Sorry. Wrong. Hey, it is. Sorry. A moment of blankness. Or hopefully get it right. I'm a little bit confused by this as well. Sorry about that. Very confused. So let me. What's the definition? Sorry, I'll have to think about this. Roughly speaking, it's the same thing as, on the one hand, you just forget about the additional P torsion, on the other side, you quotient by this subgroup order P, but then I'm a little bit confused by this N. Oh, my bad. Sorry. That was a stupid mistake. My bad. Now I UP is relatively easy. So introduce some sort of, maybe call it UP. My bad. We don't need all these. Sorry. A moment of blackness. What is the level of this thing? Shoot. I don't remember. I apologize for this, but you can define things this way. You can define something. So let's jump over. I'll think about that and send you a note. Similarly, you can define a map on the Jacobian. And also for any D in this, I can define the diamond operator. Extending the point EP to E, comma D times P. So this will give you a diamond operator. Apologize for that. More generally, I want to consider a natural map. So see, all these operators will act on this, module space module forms, and therefore, in induce the action on the Jacobians via this sort of correspondence way. So now I have a Z. I consider a gigantic algebra consisting of all these operators you can think of. I want to map that to endomorphism Jacobian, which of course will be will induce the endomorphism of the lattices. Okay, we consider this. So each of the operator will act on this, and by general, you can check that somehow these operators will commute with each other, because they already kind of commute with each other on the differential, on the sort of module form. And this guy is again a commutative algebra. It's a gigantic commutative algebra with infinite many generators. But when you map it on the right-hand side, this guy is, you see that this is a complete curve. The first homology group is finite rank over Z. So this is finite rank over Z. So if you look at sort of the image of this one in here, this is called the Heck algebra. So the finite Heck algebra. Which is finite over Z. So instead of the Heck algebra will be some sort of integral version of what we know about module form that encodes all this data. Let's make it even more sort of precise. It's a perfect pairing. If I have a sort of it's a finite algebra, which is an algebra, finite over Z. If I base change the algebra from Z to C, there's a more explicit way of saying how that gives you information about space of module forms. So there's a perfect pairing between this Heck algebra and the space of module forms. By sending, if you have some Heck algebra, let me call it T, and you have some module form F, Katz form, I just send it to, you can apply this Heck algebra or this operation on F, and then take the first coefficient of the Q expansion. Proof. If you want to show this is a perfect pairing, you just need to show it doesn't degenerate in each of the factors. So let's see. Let's prove the non-degeneracy at the module form side. That's to say that if my S, if I have a modular form such that for any T in the Heck algebra, A1 of Heck algebra of F is 0. Well, then there's following Heck algebra called Tn. It does the following. So whenever you have whenever you apply Tn to F, the first coefficient becomes An of F. And because we said, okay, for any Hecke operator, T of f is A1 of T of f is 0, so this is 0. So that means in the Q expansion, f is 0 expansion, so f is 0. So let me say a little bit about how to construct this Tn here. It's not that bad. So we just didn't have time to introduce these Hecke operators where this n is not a prime. So this Tn is defined by the following. If Mn are co-prime, I just define Tnm to be Tn times Tm. So enough to define Tn when n is a prime power. So if T divide n, Tp to the k, just Up to the k. This is all standard, right? Which is something you should learn for when you learn modular forms somehow. And Tpk can be inductively defined by this. Or at least you should have seen it. So you have these type of sort of Hecke operators whose effect on a modular form is that when you hit the modular form, the first coordinate will be the original nth coordinate. Sorry, nth coefficient. Choose the nth coefficient. Okay, that's one thing. So non-degeneracy at H1. Good. So now I prove the non-degeneracy on the other side, H1. So if I have a Hecke operator such that for any f, let me just simplify to S2, that A1 Tf is 0. Okay. Then I know the following. So if I do T of this, so I have this particular Hecke operator Tn. Remember, this Hecke algebra is a commutative algebra, right? So, anyways, so I first do this. So T applied to this Tn of f. So Tn of f is another modular form, constant form. And we said my operator T has the property that for any constant form, A1 of T of that is 0. So it's 0 by definition. But then on the other hand, this is this Hecke operator is a commutative algebra. So that's the same thing as I'm allowed to swap them. So that means that my sorry, I'm going to say then for every f, comma, I apply A1 of this. This Tn of f is another form anyway, so it's 0. I can swap T and Tn. After I swap, I get An of Tn. So what I know is that for any f in this, if applied to T of f, all the Ans will be 0. So that means Tf, the entire Q expansion is 0. So that means Tf is 0. So this says that T kills all f in S2. So that means it's Hecke operator 0 because it's at 0 at the moment. None. Just uses the fact that Hecke algebra is commutative. Now what we have here is that, let's look at the picture we have here. Maybe I should do, so this is a check. It's a bit annoying. Why don't I change to cohomology version? Avoid this issue. Okay, because and most of the Jacobi will also induce this, and most of this one here. Okay, so what do we have here? So this one. So what we have shown is that we know that this H1 and C is free. Will act on this one by Haeckelberg action. Moreover, we have this perfect pairing. Not only it acts on it, but we have some sort of perfect pairing. So therefore, basically, it induces. I guess let's do check. I'm a little bit confused by whether I want to do check or not. Maybe let's do check. So a correlate of this is somehow, at least as C vector spaces, this H1C is isomorphic to the dual of S2, right? So this will imply that H1C is isomorphic to S2 dual. Yeah? And also this H1C will act on this one. The action is sort of compatible with this pairing. If you act, somehow basically just act on that. And so therefore this will tell you that this as a H1C module, this is free module. Free of rank 1. And in a similar way, this side, I don't know how to say this, how maybe bar module. Whatever that means. Okay. So each one of them is as H1N module, essentially H1C module, is free of rank 1. So that should imply that on the left-hand side, because of the isomorphism, on the left-hand side, this is the H1. If you without tensor Q, without tensor in C, at least this is this module. At least this is flat of rank 2. Right? And because tensor C is going to be sort of free module of rank 1 and 1, so 2, rank 2. So without that, I at least know it's flat of rank 2. Okay. But on the other hand, this H1N tensor with Q is finite dimensional. Because H1 of N is going to be finite over Z, so when you tensor with Q, it's finite dimensional over Q. And all such rings are Artinian. Ring. On any local, a semi-local ring, I guess, a tuning ring. Anyways. A flat is the same thing as free. So this is free. Of rank 2. I mean, there are many ways to prove this. I'm just being lazy. But I want to make a remark that the integral version might be bad. Badly behaved. If you don't tensor with Q, this module might be very bad. In fact, that's one of the reasons why we need to use this sort of Taylor-Wells method just basically to avoid these sort of bad situations. So here's one of the sort of corollary of this. Because of the isomorphism and because of the Hecke algebra action, we see that when we say, okay, normalize eigenform F S2, let me say gamma 1n, that's basically a bijection. What I mean by normalized eigenform, basically for each Hecke operator, I give it a eigenvalue, right? So that's the same thing as homomorphism called lambda f from H1f. How this Hecke operator would act on these space model forms, we'll go to see. Basically, leaves a little space here. So what we're doing here is that I have this multiple format, so I'll map to the homomorphism that send TP to AP if P does not divide N, and the UP also to AP, P divide N. And oh, now I understand why I wrote a little bit differently. I wanted the eigenform. Well, if it's eigenform, I also want it to be an eigenform for the diamond operator. So this diamond operator will act by this chi. Okay? But then all these values, this will map to C. But there's one thing we should know, is that this H1 of n is a finite dimensional vector space over Q. We'll map a finite dimensional vector space over to C, a homomorphism. Or sort of a finite, I guess, Artinian algebra over Q to C. This must go to, well, QF. This is all the Q adjoining all these values. So Q adjoining A1, AN. All these eigenvalues. But then this is, because this, on this side, and this must be surjective. And this side is sort of finite dimension over Q, so this must be also finite dimension over Q. So this must be finite dimension. So this shows that not only these eigenvalues APs, they are algebraic integers. But even if you put all of the APs together, it only generates a finite dimensional extension of Q. So not only adjoining one of the APs, you get finite dimensional thing. Adjoining all of them, you get a finite dimensional thing. Moreover, whenever you have a homomorphism like so, I want to define, okay, so this will give you a quotient of J1 of the Jacobian. So the way this is done is following. So whenever you have a homomorphism, we can let IF to be the kernel. I mean, basically, I want to quotient out by, I want to take sort of the lambda f isotypic component of, I mean, somehow this H1n also act on this Jacobian. So I want to take the lambda f isotypic component of that. To actually do that, I have like a few lines. Let me finish. So I take the kernel of this Hecke algebra going to C by given by this eigenforms. So I get somehow an ideal of this Hecke algebra. So I just define AF to be J1 of F, quotient by IF times JF. So this will be the literally isotypic component of this. If you spell out what this means, this is the S2 of gamma 1n, taking the lambda f kernel, and then dual. Because I mean over here I have to take quotient. On the dual side I have to take lambda f kernel. So namely those elements which are killed by any element in IF. Here I quotient by x1 c. Quotient by IF h1. So this is going to be a lattice inside of here. So this will be some complex vector space, and this will be a lattice inside of that. Let's be a little bit more precise. That's 3 lines. First line, then this is a bit of variety. Overkill this overkill we'll see that next time of dimension QF, the degree of QF over Q. But that's relatively easy to see in the sense that over Q I have the perfect pairing between Hecke algebra and the S2. So if I have the precise lambda F isotypic component of S2, which must have complex dimension, precisely the degree of QF over Q. And also the Galois representation associated to F is Tate module of this, and now I have to take cyclotomic inverse. This is my normalization. And final remark, I think it's correct. The QF is always a totally real field, or a so-called CM field. So CM stands for complex multiplication. This is a quadratic, totally imaginary. Quadratic extension of a totally real field. Sorry, totally real field means that all the complex embeddings are actually real embeddings. And a CM field means that it's a quadratic extension of the totally real field, where at Archimedes place always change R to C at each of the arguments. Okay, stop here.